Welcome back. So let us now consider the definitions of velocity and speed. Okay, velocity and speed. Still dealing with kinematics of particles and of course rectilinear motion. So the definitions here will be general and of course specifically applied to rectilinear motion. So we say that rectilinear motion simply means the path followed by the body is a straight line, or the trajectory of the body is a straight line. So we're using x for reference here. So this defines the position of the body at any time t. So if the body is at this point, we just find out what is the position coordinates at this point. Okay, so we have said that if at some time t the body has some position x, okay, let's say this occurred at some time t, and then at a later time t plus delta t, the body has some position x plus delta x, and this is at some time t plus delta t. We have seen that the displacement of the body is simply this vector, okay, that actually goes in this manner from the initial point to the final point. So that is the displacement of the body, okay, and we call that delta x, okay. This gives us the displacement of the body. See that displacement is simply the final position coordinate in this case minus the initial position coordinate, and its sign will tell us the direction. So if it has a positive sign, this means the body has moved in the positive direction. The body displacement is directed to the right in this case because the positive direction is to the right. And if it happens to be negative, it means that our x2 is less than x1, which is what happens when the body moves to the left. Okay, so the sign of this in this case, in the case of rectilinear motion, the sign of delta x tells us the direction of displacement. Okay, so what is meant by velocity and what is meant by speed? So let us start with velocity. So in defining these terms, we will sometimes qualify them. Okay, so we can have average velocity, for instance. So pay attention to this. When velocity or speed is qualified, then we have to follow the implication of the qualifying term. That is, if we say average velocity, then we have to consider the implication of average. Okay, and if they are not qualified, that is, if I just say velocity, velocity used alone naturally implies instantaneous velocity, not average velocity. So, okay, so let me quickly write that before we begin to discuss the meaning of all of this. Okay, so we will discuss instantaneous velocity as well. So before we begin to examine their definitions, let us clarify some things. So we will also talk about, of course, average speed, okay, and instantaneous speed. Instantaneous speed. So when we talk about, when we just say speed, okay, speed without any qualifying term now, without putting average there, okay, is equivalent to, it just means instantaneous speed. Please and please have this in mind. It is very, very, very important. Okay, and if we just say velocity without any qualification, it's equivalent to saying instantaneous velocity. So by default, velocity implies instantaneous velocity and speed implies instantaneous speed. So if I wanted you to get the speed of the body at a given time, I would not necessarily have to say instantaneous speed. You should know I'm implying instantaneous speed when I have not qualified it. Okay. But when I need you to find, or you're required to find average velocity, that has to be explicitly stated. Okay, so you would not go ahead to just find average velocity because you were told to find velocity. No, you were told, if you are told to find velocity, that means you are told to find instantaneous velocity. Okay, so now let's get into their definitions. So firstly, we'll talk about average velocity. So when we say average velocity, of course, velocity is a vector. Okay, velocity is a vector, whether it is average velocity or instantaneous velocity, and speed is a scalar quantity. So that means that we should expect some measure of direction when you're talking about velocity. Okay, speed is a scalar quantity, whether it is average speed or instantaneous speed, it is a scalar quantity. Okay, so now let's go ahead and deal with this. So when we say average velocity, okay, which we denote as v sub avg, okay, for purpose of this course, we use v sub avg, okay, average. It is simply the displacement delta x divided by the time taken delta t. So the time interval during which the displacement occurs, okay, that's delta t. Of course, time interval will always be positive, so this one cannot be negative. We're not working back in time, okay. That's not our business in this course. Whether you can work back in time or not, it's not our business in this course, okay. So delta x is the displacement. We've discussed that already. So we know that displacement is a vector. We said that the direction of the vector is implied by its sign. Okay, so that means this average velocity also is a vector, and the direction of the vector will be implied by its sign as well, which will of course follow from the sign of the displacement, because the sign of the time difference delta t is always positive. Okay, so this is the meaning of average velocities. If I'm asked to find average velocity between a given time interval, then what I need to know is the displacement within that time interval, and then just take the displacement and divide by the time interval. So it's as simple as that. Okay, so for illustration, we'll take more reasonable examples. Okay, as we proceed with this chapter. Uh, for now, this is just for illustration, a very simple case now. So let's say that the body was at a time t equals to 0. Okay, at time t equals to 0, the body was here. This is position coordinates. Okay, so let's say that the body was here and the position coordinates here was 5. Okay, this is x coordinates. Let's say this is in feet. Okay, and the coordinates here was 5, and then later on the body moves in this direction so that the coordinate here is 2. Okay, and let's say this happened at time t equals 2 seconds, and this occurred at some time t equals say 4 seconds. So in this case, how do we get the displacement? So we just get our delta x. So we know that this was the initial time and this is the final time. Okay, so if this happened or this occurred at time t equal to 2 seconds, it's obvious that the body was moving in this direction. Okay, now it does not really matter how the body got to this point. It may happen that the body had moved in this manner. Maybe it started from here and actually had to move this way and then turn back to get to this point. Okay, it doesn't matter how it got there. Our business, as far as displacement is concerned, is what is the initial position and what is the final position. So once that is ascertained, then we're good to go. We don't have any business with how it got there. Okay, so now, if we are interested in delta x, that is the displacement, then that is going to be equal to the final position x2 minus the initial position x1. So what's the final position? 2. That's the coordinate. The final position coordinate. So it is 2, okay, minus the initial position coordinate, which is 5. So this is going to give us minus 3. Of course, the unit is feet. Okay, so this is a vector. Yes, is this a vector? Yes. Now the vector here is simply defined by its direction is simply defined by its sign. Its sign is implying that it is to the negative coordinate direction. So this is the positive direction of the coordinates, that is from the origin to the point or to the side where we have the label, and the negative would then be in this direction. That means the body has moved leftward. Okay, the displacement is a leftward displacement. So obviously that is true because the body was initially here. Now, displacement has nothing to do with where it went through. It means the overall displacement is simply from this point to this point. All right. So now That is delta x, and of course delta t would simply be the change in time. That will be t2 minus t1, which will always be positive. So t2 is 4 and minus t1, which is 2. So this is just 2. So having obtained this, then the average velocity v average is simply going to be um, delta x over delta t, delta x over delta t, which is going to be minus 3 divided by 2. Okay, of course, this is in seconds. So this is basically going to give us average velocity to be equal to minus 3 over 2, that's minus 1.5. This is in feet per second. Now, the negative sign. Now, the average velocity is a vector. Okay, the negative sign implies in this case of rectilinear motion, again, please have that in mind as you go through this. In this case of rectilinear motion, the negative sign implies that the direction is the negative coordinate direction. So we say that the positive coordinate direction is rightward, the negative coordinate direction is then leftward. So this implies that the average velocity, now recognizing that it is a vector, is equal to 1.5 feet per second. Now we will interpret the negative sign. That means it is in the leftward direction, and then this will be the way to present the result. Okay, so this is our result. I'm trying hard to not cross that line. Okay, yep. So that is average velocity. Life is as easy as that. So must recognize that it is a vector. So, like I said in the previous chapter, that if you are given a problem to analyze and what you have been asked to find is a vector, you must recognize that your answer is not accurate until you have specified the direction of that vector. Okay, so that is that for this illustration. I believe you know now what average velocity is. Now let's talk about instantaneous velocity. Instantaneous velocity. Instantaneous velocity. So when we say instantaneous, it means at an instant of time. So this one is not average over a certain interval of time. This is at an instant of time. That means the interval is extremely small. So you can say the interval is nearing zero. So if there is a possibility of having an interval that is zero, okay, there's no possibility of that. So we say it is extremely close to zero. And what we mean by that is that we are not trying to observe. Okay, we're not trying to observe the motion at maybe two different time intervals. Let's say, okay, what is the position at this time interval? What is the position at this particular instant of time? Then what is the position 10 seconds later? Then let's take the average, okay, over that interval. That's basically what we did here. And that's why we call this average velocity. Okay. But in the case of instantaneous velocity, it means that we just want to observe that at this instant, how fast is the body moving? That is, provided that at this instant, the rate at which the body is moving remains the same, then how fast will it continue to move? Okay, so that's basically what instantaneous velocity tells us. And this will be sorted for us by some of the mathematical concepts we have examined in the past, which is the concept of limits. So basically, the instantaneous velocity, just noted as v, okay, we know it is a vector, even though we are using some scalar representation here because we just want to get some algebraic number, okay, and then when we get that, we will interpret it properly as a vector as we should. So this is v, it is going to be equal to the limits of delta x, okay, over delta t. It is still having to do with the displacement and the time interval, but now the time interval is approaching zero. So it is the limit of this, okay, as delta t approaches zero. So that means at an instant of time, let's just observe, pam, at this point when I cause this body moving. If the body was just to maintain how fast it was moving at that point, at what velocity then will it continue to move? Okay, so that instant of time is captured by saying delta t is approaching zero. That means it is extremely small and almost zero. Okay, so if that happens, Then what will be our result here? From elementary calculus, we know that the limit of delta x, or say delta y over delta x, as delta x approaches 0, is just the y dx. So this is just definition of the derivative. So by that, we say that v equals the x dt, in this case of rectilinear motion. So it is simply the derivative of x with respect to time. That is the derivative of the position coordinates. Don't forget, x is position coordinates. It's delta x that is displacement. Okay. So this is the derivative of the position coordinates with respect to time. And if you like using some other symbol, we can say v is equal to x dot, in this case dot, implying derivative with respect to time. So this is the instantaneous velocity, or just the velocity of the body. So for us to get the instantaneous velocity, or velocity at an instant of time, then it means we should have x firstly defined as a function of time. That is when we can clearly carry out this differentiation. Okay, so that means to define the motion of the body, we need x to be given as a function of time. So when we have x as a function of time, definitely we'll be able to get its velocity, we'll be able to get its instantaneous velocity. Of course, x as a function of time simply means we're able to get the position of the body at any time t. If we're able to get the position of the body at any time t, we say the motion of the body is defined, of course, because with that we can get any motion parameter with that expression. So before we can get the velocity, the instantaneous velocity, we need to know the position of the body as a function of time, or some other details that help us actually obtain the position of the body as a function of time. But just bear in mind that the instantaneous velocity is given by the x, the t. Okay, so from what we have done here, we saw clearly that average velocity being negative implies that the body is moving in the negative direction. So if you look at this now, if instantaneous velocity is, let's say instantaneous velocity is 0, for instance, what does that mean? If velocity is 0, now just pay attention to this expression here. This says v is equal to dx dt. So if v is 0, it means the x dt is 0. That means the rate at which the position changes is 0. So what will be the implication then? If the position is not changing, that means the body is at rest. So if the position is not changing, this is the position coordinate, okay, that tells us how where the body is located at any time t. So if the position coordinates is not changing, so let's say we have something like this. This is the position. The body is just here, okay, or the body is just at any position, but the position coordinate, the x coordinate is not changing at all. If it is not changing, it means the body is at rest. So if this instantaneous velocity is 0, it means the body is at rest. But that is not true for average velocity. I mean, if the displacement is 0, average velocity will be 0, and that would not imply that the body is at rest. Okay, so let us observe that if v, which is instantaneous velocity, is 0, it means that the body is at rest. The body is not moving because x is not changing. That is the meaning that v is the rate of change in x, which is the position coordinate of the body with respect to time. So if v is 0, then x is not changing. That is, the rate of change of x with respect to time is 0. That means that the body is at rest. Okay, so that's one. Another thing is this. Let's consider what happens if x is positive. Sorry, if v is positive. If v is positive, that means the rate at which x is changing is positive. So if something is changing at a positive rate, that means it is increasing. So if v is positive, that means the position coordinate is increasing. So how would that happen? If the position coordinate is increasing, it means that at that instance, the body is moving in the positive x direction, because it has to be going towards this positive side for this coordinates to be increasing. Okay, so we say that if V is positive, that's if V is greater than 0, the body is moving in the positive direction. In the positive coordinate direction. So that is that about that. Okay, so what happens if v is negative? That means the rate at which x, which is the position coordinate, changes is negative. If there's a negative change, that means there's a decrease. So that's if that x coordinate is decreasing, let's say it was initially 5 and later became 4, that is a decrease. Then it has to be that the body is moving in the negative coordinate direction. So we take note of that as well, that if v is negative, that's less than 0, the body is moving at that instant. The body is moving in the negative, in the negative, in the negative coordinate direction. So altogether, we can see that if the body is moving in the positive coordinate direction, v will be positive. If the body is moving in the negative coordinate direction, v will be negative. If the body is at rest, v will be 0. That means that the instantaneous velocity helps us capture the direction of motion as well. So the body is moving in the positive direction at a certain instant, the v will be positive. The body is moving in the negative direction, v is negative. The body is at rest, v will be 0 at that instant. At that instant. So that is some primary things to know about the instantaneous velocity. Okay, so now let us go ahead and discuss speed very quickly. So in the case of speed, that will be Roman figure 3. Let us also start with average speed. So when we say average speed, so how do we denote speed now? Let's try to invent some expression for speed. I'm trying hard not to use v. Okay, so let's say that we want to use speed. What can we use for speed? Let's say we're using u, okay, for speed. Okay, average speed, UAVG. It is simply the distance traveled over the time taken. So it is simply distance s, or say delta s if you like, all over delta t. Um, I don't want to say distance. I don't want to say delta s. That doesn't look so good. Doesn't look so good to use delta s. But for lack of an alternative, let me use delta s. Distance. Okay, this is implying distance traveled divided by time taken. That is average speed. Distance traveled divided by time taken. Now, we have discussed extensively in the last lesson the differences between distance and displacement. So since distance is not equal to displacement, we know that average velocity is not equal to average speed. So average speed is not magnitude of average velocity, because speed and because distance is not magnitude of displacement. So you should recall that we discussed that previously, that for you to get displacement, you just need the initial position and final position. So if the body was initially here, so it may happen that the body as initially, we illustrated it in the last lesson, so this is just for refresher. So the body is initially here and then finally here. So in the case of displacement, we're just interested in the initial and final position. So this is going to be our delta x. Okay, and distance. In the case of distance, we're interested in how did the body get here, that is the total length of the path followed by the body. So it may happen that the body has gone in this direction first, then turned back, then got here. So in this case, distance is simply the length of this part, okay, plus the length, okay, of this. So our distance is just going to be this distance s1 plus this distance s2. So that's why I said it's not so good to just use this here. So let me use s so that we don't mistake this. All right, so this is just the distance it has traveled is just going to be the total length of path that the body has followed. So when we have that, then we know that it is not necessarily equal to the magnitude of the displacement. So definitely average speed is not equal to the magnitude of average velocity. So let us take note of that, that average speed it's generally not the magnitude of average velocity. It's not the magnitude of average velocity. All right. So that is the idea. For us to get average speed, we need to get the total distance traveled divided by the total time taken. So if we use delta S here, it would imply that at this instance, what is the total distance that's traveled from the starting point? Okay, then at this point, at this instant of time, what is the total distance that's traveled from the starting point? Then we can subtract the two. So if we interpret that in that sense, then this will be delta S. Okay, so that won't be S1. So if we know the starting points like at time t equal to 0, then we can use that expression. Okay, so that is that about that. So let's just leave it as S like that. Total distance traveled over total time taken. Okay, so now let's move on. What is meant by instantaneous speed? If we talk about instantaneous speed simply means the speed at an instant of time. Don't forget, we said that speed, whether instantaneous or average, is a scalar, and velocity, whether instantaneous or average, is a vector. So instantaneous speed would also mean the same thing that we had earlier or similar to this. It means the speed at an instant of time. So definitely, this will also mean the limit at delta t approaches 0 of delta S or S if you like all over delta T, okay, where this is the distance traveled, okay, with respect to time. So this is for a very tiny interval. The interval is approaching 0. So I need you to think along with this or reason along with what I'm about to do now. So imagine that the time interval is extremely short, almost 0. Now, let's say the body is moving on a straight line and the time interval is extremely short. So we have something like this. Let's say the body is initially at this point, and then at a later time, the body is at this point. So because the time interval is approaching 0, the this delta S here will happen to be equal to the magnitude of the displacement because it is a very small time interval. So no matter the direction of motion, because it's a very short interval of time, like almost 0 or even 0 if you like, then no matter what happens, the distance will be so short that it is just the same as the magnitude of the displacement within that extremely short interval, like a flash. Okay, so no matter what is happening, you cannot possibly have a situation where within that short interval, this thing has gone around like this, and then it comes here, and so the displacement is 0, and then the distance is extremely large. No, at a very short time interval, that is practically or nearly 0 time interval. Then for that short time interval, the distance okay at that for that short time interval is going to approximate the magnitude of the displacement right there. So because of that, yes, of course, we will still write this using our rules of calculus. We recognize that the speed, instantaneous speed, is actually just the s dt, where s will be some function that tells us the distance traveled as a function of time. So if we know that, yes, we can use this expression if it tells us the distance traveled as a function of time. So in this case, because the time interval is extremely small and nearly 0, then the displacement, the magnitude of the displacement will be equal to the distance traveled within that extremely short interval of time. So because of that, we recognize that instantaneous speed is magnitude of instantaneous velocity. So please take note of that. Instantaneous speed is magnitude of instantaneous velocity. Instantaneous speed is generally the magnitude of instantaneous velocity. Okay, so from what we said when we started, you should know now that if I just say speed is magnitude of velocity, that is correct because I have told you that when we just say speed without qualification, we mean instantaneous speed. Or we just say velocity without qualification, it means or we mean instantaneous velocity. So it is correct and acceptable to say that speed is magnitude of velocity. However, we must know that that does not apply to all kinds of speed. So we know that average speed is not magnitude of average velocity for the same reason that distance is not magnitude of displacement. Okay. However, at a very short interval of time that is nearly zero, then no matter what happens, our displacement and velocity will be the same. That is recognizing the same thing we said when we discussed distance and displacement, that when the body moves on a straight path and there is no turning point, it doesn't turn back or anything, then we recognize that in that under that condition, under that special case, distance will be equal to magnitude of displacement. So if the time interval is extremely short, then the no matter what happens, if the time interval is very short, even if the body was moving on a curved path, if the time interval is very short, then whatever this displacement is going to be is going to approximate the distance. Okay, whatever it is, wherever it is located, the displacement is going to approximate the distance. So that is the idea. So if you pick a very short interval and you connect this point to this point here, it is going to approximate the distance. Okay, displacement is going to approximate distance. That is why we take instantaneous speed to be generally just the magnitude of instantaneous velocity. So if we don't know a function for position with respect to time, what we simply for the distance traveled with respect to time, but we know the equation for the position with respect to time, which is x with respect to time. Please take note of the difference between the x here and s as used here. S is implying distance. Okay, so if we have s as a function of time, then we can do the s dt and it will give us the speed, okay, as a function of time. So we'll get the speed at any time. T, of course, it is a scalar, so it is just some magnitude. And if we don't know distance as a function of time, once we have once we have position as a function of time, we can differentiate it to get velocity as a function of time. And then when we find the velocity at a given instant, let's say at time t equal 5 seconds, then we know its magnitude is just going to be the instantaneous speed or the speed at that point. Okay, so that is that about that. This has been developed for the case of rectilinear motion, but the concept actually apply generally, even if the motion is not rectilinear. So the differences will just be in the symbols, in terms of how we represent the vectors. So here we have represented V as though it was a scalar, and that was acceptable because we said that the sign of the algebraic whatever results we get from here would imply the direction, okay, and from that we would already be able to tell what the direction of the velocity is, because in this case it's either positive or negative, it's either to the right or to the left. Okay, so that is that about that. So you should know now that because instantaneous speed is a magnitude and it has to do with distance, it will always be positive. So it cannot be negative. It's some magnitude. Just as average speed is also some magnitude, because distance is total length of path. You can't have a negative length. Okay, it is total length of path followed by the body. So distance cannot possibly be negative. So um, average speed also can never be negative. It is always a magnitude. All right. So I believe with these few points of mine, I've been able to convince you and not confuse you about the differences between speed and velocity. I'll see you in the next lesson as we discuss acceleration. Thank you for watching.